Welcome back to structural dynamics class. So in this class we will study damped forced vibrations. System is vibrating because of the application of the external force which is dynamic in nature along with the damping present in the system. So how the behavior of this system will be, so that we are going to study. So first, general equilibrium equation, that is equation of motion, and then this. So we have already studied three types of vibrations, that is undamped free vibration, damped free vibration, undamped forced vibration also we have studied. Now in this class we will study damped forced vibration. So damped forced vibration looks like this. So where mass of the system is given by m and then stiffness is given by k, and also damping is present in the system, and then external force is applied, that is sinusoidal force P0 sin omega t. P0 is the amplitude of the force and omega is the frequency of the force. So equation of motion looks like this one, the complete equation of motion. So this equation of motion consists of like two parts. Equation of motion has on right hand side non-zero term. So since it has non-zero term, we call it as non-homogeneous differential equation. This is linear differential equation with constant coefficients, non-homogeneous type. So if we divide this equation by mass, so we get u double dot plus 2 zeta omega n u dot plus omega n square u and p naught by m into sin omega t. So this omega is forcing frequency, this omega n is a natural frequency of the system which depends on system properties, that is stiffness as well as mass. So solution, since it is non-homogeneous differential equation, so solution has two parts, one is complementary function and the second one is particular integral. So first of all, let us find out how the particular integral looks like. So since sinusoidal wave is applied as a forcing frequency, so we can find the solution, or we can assume the solution to be of two components, that is c cos omega dt and d sin omega dt. So this omega d is a damped natural frequency. Okay. So u complementary is cos omega dt sin omega dt. Sorry, this one will not have damping present in this one. If we differentiate it with respect to time, so up, that is omega d c sin omega t omega d into c cos omega t. Substituting in the equation of motion, we get c constant and d constant. Then if we write it back, the solution of the differential equation, that is linear differential equation with constant coefficient, non-homogeneous in nature, the response will be ut is equal to u0 sin omega t minus phi. So here it is showing phase. So phase is like when we are applying force, if you can look at it. So this is a cantilever beam and then a person is standing at the end and slowly like sitting up and down, and then the rod is deflecting. So a rod is also oscillating because of the person's moving up and down. So what happens is, for some time the motion of the person and the motion of the rod or the cantilever plank will be in phase. Suddenly at some point of time it goes out of phase. As the person is trying to come down, the plank is applying force in the upward direction. So that is called out of phase kind of motion. So this phi denotes that. So in phase, out of phase. So in phase is less than 90, out of phase is more than 90. So the complete solution looks like this. It has two components, one is transient motion and the second one is steady state motion. So total response, if we plot, it will be this red dotted line is a steady state response, and the transient motion along with steady state motion is given in the form of blue line. As you can see in this one, blue line is slowly merging into transient. So because this transient motion which is responsible, which is coming from the initial conditions, will remain only till some point. So when damping is present, it will die out soon. So in overall summary, if we look at it, equation of motion, simplified equation of motion, and the solution constants, and then finally A cos omega dt, B sin omega dt, and C cos omega plus B sin omega. So this omega is a forcing frequency, and this omega d and omega d is damped natural frequency, and this is the response of that. And then if we take the example problem, same example problem what we have discussed earlier. So a generator of 1 ton is placed on a concrete plank of width 500 mm and length 2 meters and thickness 120 mm. Find static and dynamic deflection of generator running at 2000 rpm. Use M20 grade concrete. Assume damping ratio at 5% of critical. So now damping is present in the system. Earlier case damping is 0. So if we derive or find out mass of the plank, this is volume of the concrete plank, and then density of the concrete, that gives us weight 3 kilonewton. So that is equal to 300 kg, and then modulus of elasticity of that is 5000 under root FCK, which is 22,361 Newton per millimeter square, and moment of inertia I is equal to BD cube by 12. So B is 500, width is 500, and depth is 120 mm by cube by 12, that is 72 into 10 to the power of 6, and the stiffness of the plank is 48 EI by L cube. So when we substitute all the above values, we get 9.6 into 10 to the power of 3 Newton per millimeter, or 9.6 into 10 to the power of 6 Newton per meter. So if we calculate the natural frequency, the omega n, which is under root k by m. So this is 9.6 into 10 to the power of 6 by 300. So we get 178.9 in radians per second. This is a natural frequency of the system. As the machine is operated at 2000 rpm, so we can convert that rpm into radians per second, that is 2 pi by 60 into given rpm, so which we get 209.4 radians per second. So the frequency ratio, you will use it. So frequency ratio R is omega by omega n, so this is 1.17. so this is slightly higher than the resonating condition. Now if we find the static deflection, which is P naught by K, so that is equal to 10 into 10 to the power of 3 divided by 9.6 into 10 to the power of 6, that gives us 0.001 meter, which is 1 millimeter. Then dynamic deflection is U is equal to UST, static deflection component, multiplied by dynamic amplification factor. So the dynamic amplification factor in this case is 1 by 1 minus r square whole square plus 2 zeta r whole square under root. So if you substitute all these terms here, this is without dynamic part. If you substitute all these terms here, we get if you take zero damping in this case, so we will get 2.71 millimeter. But let us look at the case with the 5% damping. So when we put 5% damping, and then when we increase the rpm from 0 to 2000, so how it looks like, let us see. 0 rpm, then forcing frequency is also 0, then r is 0, rd will become 1, and if rpm increases slightly, which is 100, so frequency is 10.47, 0.5059, and again it is very near to 1. So as when it increases up to 1500, omega is 157 and 0.878 is r, and 4. So as you can see, this is like 4 times more than static deflection. So you can see here u0 is equal to ust into rd. So that means rd is equal to u0 by ust. So that means it is 4 times more than static deflection. And when it comes to 1800, it is 188. It is above 1.053. So that means what, in between this one something is happening. So what is that? A resonating condition is happening, but still immediately after that displacements have reduced. Before that displacement is higher, so that is amplification is higher, but on the reducing direction, reducing path. You can see this one. So if we plot that frequency ratio R and RD, so this resonating frequency is 1 and this is static deflection. Okay, RD is U0 by UST. So here if it is 0 at static, it is 1, and then it goes like this up, and then suddenly it comes down like this. Okay. So what damping does is, damping controls the amplitude of vibration. If it is undamped vibration, then it would have been something like this. It will go to infinity and make the system break during the vibration. Summary: what we have discussed in this class. We have discussed how to find out the solution to damped forced vibration, where forcing frequency is omega and natural frequency is omega n, and damped natural frequency is omega d. So we get a equation consisting of two parts, one is transient part and steady state part. So transient part will die out because of the presence of damping, and steady state part will continue. And we have studied one example problem also of how we apply this damping in damped forced vibration.